Now, this is an extremely important and fundamental concept in all of physics, not just in mechanics. And we will see that it has applications as you move through this year of physics, not just to motion, but to thermodynamics, electric systems, etc. So the statement of conservation of energy is that energy cannot be created or destroyed, only transferred from one type to another. So if we are going to choose our system, our so-called system, to look at where all the energy is. So if we are just smart about it and we choose our system to include all types of relevant energy to whatever problem you have, so pretty much just include everything in your system, all types of relevant energy, then we can say that the total energy in a system is going to be equal to a constant. Now your system can have multiple objects, etc., but that the total energy is always going to be a constant. So if your system is, for example, the entire universe, this still holds true. Total energy is a constant, and you just have to look enough places and account for all the energies. So we've talked in class about all these different types of energies. And so if we remember, the ones that we're going to be able to quantify in our problems, there's going to be 4 of them. We're going to have kinetic energy, we're going to have gravitational potential energy, we're going to have elastic potential energy, and then we're going to have internal energy, which remember is essentially the kinetic and potential energies of atomic motion. So you rub your hands together, that's kinetic energy. They get warm, and that is because you actually have all of the molecular motion and these kinetic and potential energies on that very small scale. And then that's quantified as internal energy. When we do thermodynamics, we'll come back to that idea. All right, so you'll have internal energy only in a system that we're going to quantify only when it's friction. We're not going to quantify it too much for air resistance, although we could figure out how much is lost to internal energy in some more complex system. So these first, the kinetic and the potential, are what are called mechanical energies. So sometimes people will talk about conservation of mechanical energy only. That then is assuming that you have a system that has no losses to internal energy. All right, so there's our statement of conservation of energy, and it's, like I said, extremely far-reaching. And the way that it's going to work is very similar to how Newton's second law worked, where you had a fairly simple equation with a lot of applications. And so you're going to use this statement of conservation of energy to develop your own equations for each problem. Okay, so what we can do is if the total energy in a system is constant, most commonly you're going to talk about it at some time 1 and some time 2. So you would say the total energy at some time 1 is going to then be equal to the total energy at some later time 2. So what you do is you take the sum of all individual energies, and that's then what's going to be equal to a constant. So you might, for us, when we have these 4 types of energy, say that you never really start with internal energy in your system. It's always something that only is after some event has occurred. So you're going to start with your kinetic energy plus your gravitational potential energy plus your elastic potential energy. And these would all be your energies at some time 1, right? That's the subscript 1. And again, it's going to be all. So if you have multiple objects, you would then have a kinetic energy for each one, a gravitational potential energy for each one, etc. So all the energies at time 1. And then that's going to be equal to the energies at time 2. Some kinetic energy, K2, plus UG2, plus the elastic potential energy. And then now, if you had some friction, or air resistance, then you might have some internal energy. So then here you have all mechanical energies at a later time too. So this is the later time because it's after you've already created some internal energy. And again, this is the amount that is lost to friction in collisions, etc. So in the extreme case, say I drop a piece of clay on the ground and it stops. So energy is still conserved in that situation, right? Initially, if I drop it from rest, my kinetic energy is 0. There's no spring, so I don't have elastic potential energy. So I have some gravitational potential energy of this piece of clay. That's my initial time 1. The later time 2, well, it's not moving. It doesn't have any of these mechanical energies. So all of that initial gravitational potential energy has now turned into internal energy of the system. The molecular and atomic motion from that collision and the atoms involved in it and near it then are taking, and all that energy has been transferred to them, and it's now in the form of this internal energy. But still, total energy is constant. Okay, so we can now talk about some of the terminology. One of it is going to be this idea of an isolated system. So an isolated system is the type where we pretty much want to choose all the time, where you don't have any energy that transfers outside of the system. So an isolated system means that everything is in the system. So you choose your system wisely. And so you have no energy transfer outside of the system. So again, when you're doing your problems, usually this isn't something that students get stuck on. You just make sure you include all objects, all things of relevance, everything that might contribute to your energy in order to be able to say that it's constant before and after. Okay, so I can now write down some steps for solving conservation of energy problems. Because this is really a very powerful way to solve some complex problems, even with just basic algebra. And then obviously, again, as your math gets more complex, you're able to apply this to even more complex situations. But it is, sort of one of these main principles that underlies all of physics. So first you want to identify times 1 and 2, right? You want to know when you're going to say that the kinetic energies plus the potential energies equal the kinetic plus the potential plus the internal. So you need to identify time 1 and time 2 for a given system. Sometimes that's an easy step, sometimes it's a more difficult one. All right, the second thing is you want to see if the gravitational potential energy is involved. And if it is, then you have to pick where you're going to say it equals 0. And so that's going to then depend on where you want to call y equal to 0. Now remember from our discussion in class that this is arbitrary and it's not going to change your answer, because what matters in your equation is actually going to be the change in the gravitational potential energy. So this won't impact your answer, but it's a necessary step for being consistent. So you need to then, after you've done that, write down the individual energies, and remember that energies are scalars, so this actually becomes a lot easier than some of the forces and their components, because there are no components for energies. They're all just scalars and they all just get added together. So write the individual energies for all objects in the system. So you would then have K1, K2, so your initial and final kinetic energies, UG1, UG2, the elastic, U elastic 1, U elastic 2, and then the internal energy. And for these ones, remember that you use that the kinetic energy equals 1/2 mv squared. the gravitational potential energy equals mgy. The elastic potential energy equals 1/2 kx squared, where that's the distance from equilibrium, so that x is not arbitrary. You don't get to pick where x equals 0. It'll be defined by the spring. And delta U internal from friction is going to be equal to mu sub k times n, because that's your force of friction, times the distance that it traveled. So you can then quantify all of these. And now what you want to do is set the sum of all the energies at time 1 equal to all the energies at time 2, and then solve. So again, you end up with just this single equation. You don't have components. Everything is a scalar, right? So everything is a scalar quantity, which makes it mathematically easier to solve. Okay, let's do 2 examples. The first is, say that we want to drop a ball from a height h, and we drop it from rest. And then we ignore air resistance. What is the speed at the bottom just before striking the ground? Note that you weren't given the mass of the ball. And as we know from kinematics, we don't need it. And you could solve this problem using the kinematics equations. But we're going to look at it and see that we can also solve it using conservation of energy. So let's go ahead and follow our steps. Let's identify time 1, right before we drop the ball, and time 2, just before it strikes the ground. And then we want to say that gravitational potential energy is involved. So we're going to say that y equals 0, say, at the bottom. So we can say that UG2 would be then equal to 0. All right, and now we just need to write down our initial and final energies. So we can say that K1 is going to be equal to 0, and that was because it was from rest. And UG1 is going to be equal to mgh, right, because it was dropped from a height h. And we don't have any springs, so there's no elastic potential energy. K2, the final kinetic energy just before it strikes the ground, is going to be equal to 1/2 mv final squared, and we want v final. And we've already identified that UG2 equals 0, and we're ignoring air resistance, so there's no internal energy, and that equals 0. And obviously no springs, so no elastic potential energy. So we are going to set the sum of our time 1s equal to the sum of our time 2s. So our energy at time 1 is equal to mgh, and our energy at time 2 is equal to our 1/2 mv final squared. So the initial gravitational potential energy turned entirely into kinetic energy. We can now see that our masses cancel, and we can write that our final speed just before it strikes the ground is the square root of 2gh, which is identical to what we would have gotten from kinematics. Okay, as a second and last example, let's say now we do involve elastic potential energy, and we have a ball of mass m that's compressing a vertical spring k, that has a spring constant k, some distance x, and it's going to be released from rest, and then that's going to shoot up in the air. To what maximum height does it rise? And so you want to give the height relative to the launch point in terms of the variables supplied in the problem. So it's compressing the spring by some distance x. So you know then that there's some equilibrium position of the spring, that if the mass wasn't there compressing it, it would be at. So the mass then is compressing that spring, getting it pushed downward, say, and then it's being held and released, and it will then go up. So it's some distance x here. We're going to call, since gravitational potential energy is involved, this launch point as y equals 0, so that we can say UG1 equals 0. Initially, there's no gravitational potential energy. So that's a choice that we make. If we're going to take the initial time right before the launch, and then it's going to go up in the air and then come back down, we want to find the maximum height it reaches. Well, at that maximum height, the speed is 0, just as the speed is 0 initially. So we can say that the kinetic energy at time 1 and the kinetic energy at time 2 are both equal to 0. So that's going to be at the bottom and at the max height. So we actually don't have to worry about kinetic energy in this. A lot of times that happens with these conservation of energy problems where a lot of terms are 0 and it really simplifies the situation. So we can now write out that we have initially our elastic potential energy, EL1, is going to be equal to 1/2 kx squared. And we're given k and x as part of the problem. The elastic potential energy 2 is 0 because once it's no longer compressing the spring when it's at the top, there'll be no more elastic potential energy of that system. The kinetic energies are 0, so we've already decided that the initial gravitational potential energy is 0, and we would have then the final gravitational potential energy would be equal to mg times some height h that it arrives to. And this is what we want. We want h. There's no internal energy. It doesn't say anything about air resistance. Specifically, we would have to tell you to ignore air resistance in a problem. And so we can now say that our initial energies, which is just 1/2 kx squared from the spring being compressed, turns entirely into the gravitational potential energy. So we can say 1/2 kx squared equals mgh. And again, you see how you're writing your own equations based on your situation and your analysis of the initial and final energies. And so now we can go ahead and solve for h. And now our masses don't cancel. And generally when you're working with springs, the mass will not cancel. And so you do often need to know the mass in these cases. So your final value for the height is equal to the spring constant times the distance it was compressed squared divided by 2mg. And this makes conceptual sense, right? If it was a very strong spring, then it's going to go to a larger height. If it was compressed a large distance, it would go to a larger height. And if it was a smaller mass, it would go to a larger height. More of that energy gets transferred into gravitational potential energy.